Heat sinks are commonly used to cool electronic components. They must meet seemingly uncorrelated requirements: high surface area, large cross-sectional area, and geometry that allows fluid to flow over the surface. The fractal-like geometries often observed in natural and biological systems seem to have characteristics that might meet these requirements. Coral colonies seem especially pertinent to heat sinks. They form structures that appear to maximize access of nutrients to many of the polyps which form the colony. The present project explores generating branching structures by simulating coral growth. These are a few examples of structures generated by the simulation. The coral is modeled as a mesh composed of nodes and edges. Nodes represent polyps, and edges represent the physical connections between polyps. Nutrients, modeled as spheres, move in a pseudo-random walk. This is a simple model for diffusion, a major transport mechanism for coral nutrients. Future versions might include other important factors like fluid flow, convection, and light. The random walk is controlled by spherical coordinates. The azimuthal angle has an equal probability of pointing in any direction. The inclination angle has a much higher probability of pointing straight down. When a sphere intersects a node of the mesh, that node and its neighbors grow outward. Neighbor nodes grow by an amount proportional to their distance from the nourished node, according to the Gauss function. This could be thought of as nutrient distribution between polyps. Edges that are above the initial average edge length are subdivided. This mimics asexual reproduction in coral colonies and ensures a smoother mesh. Similarly, small edges are collapsed. This helps maintain a more regular mesh, which is important for clean subdivision and 3D printing. Spheres spawn from the top plane of a box. The box grows with the mesh in order to minimize wasted time spent jittering the spheres about in space. Future versions may include the sidewalls as spawn planes, or perhaps a hemispherical boundary in place of a box. A future iteration could include computational fluid dynamics to simulate the actual conditions of a heat sink. This would diverge from simulating living corals, but the most basic growth model is preserved, that of nodes of a mesh growing according to local nutrient concentrations. After generating a structure, the model was 3D printed in ABS plastic. The model was investment cast in aluminum. This process involves pouring a plaster-like substance around the model, burning out the plastic, and then inserting molten aluminum using a centrifuge. The model on the right has a square base, which is more representative of a real heat sink application. The model on the left is a much higher quality print of the first structure. This is an animation of the simulation running in real time.